Hey guys, so today we're going to start chapter 3. Okay, chapter 3, we start really going into what a function is, and we do some different things with functions and we'll look at a project later in the chapter, which is kind of a lot of fun. All right, so objectives for 3-1, we're going to understand that a relation is a function if each element of the domain has exactly one element of the range. Okay, we're also going to look at some real-world problems and determine reasonable domains, look at constraints on the domain, and figure out really what's going on and how we can turn these words into math. So 3-1 is all about relations and functions. Okay, so our first example, remember they like to throw us right into an example and then explain what's going on. So here's our example. Our job is to figure out what are the domain and the range of the function. Okay, so notice we have this table here that they want us to talk about the domain and range. So a definition, a relation is a set of ordered pairs. Okay, a function then is a special type of relation in which each input is assigned to exactly one output. Okay, so a relation is sets of ordered pairs, so x's and y's. Another way to say a function, it's a relation in when each x has exactly one y. Okay, another way you could think of that. Each x has exactly one y. Okay, so the domain of a function is a set of inputs, and the range of a function is a set of outputs. Okay, by convention, so what we normally do, inputs are your x values, outputs are your y values. Okay. So input is your x, output is your y. Okay, and a function is a special relation in which each x only has one y. Okay, so now we can actually go back to the problem. What are the domain and the range? Okay, so domain are inputs. Okay, so our x values. So domain, label it with a D. 1, 2, 3, 4, and 5. Okay, it's just my x values, which are right here. Range, again, you're just going to list them. 11, 12, 13. Do I have to keep listing 13? No, you only need to list it once. Okay, so that's the answer to the question. So domain 1, 2, 3, 4, 5. Range is a set of y values 11, 12, and 13. Okay, so you might be thinking, wait a minute, I've got all these 13s hanging around. How is this still a function? Okay, so even though 3, 4, and 5 all go to 13, the relation's still a function such each element in the domain has only one output. Okay, basically what this is saying is you don't want any x's to cheat. Okay, each x has to be distinct. Okay, notice we don't repeat 1, we don't repeat 2, we don't repeat 3, 4, or 5. Okay, just because 13 repeats doesn't mean it makes it not a function. Okay, for a function, we only care about the x's. Okay, and I like to think of it as a relationship. Okay, so here's the boys, and we don't want any cheating boyfriends. We don't care about down here. We just care about the boys. We don't want them to cheat at all. Okay, so no cheating exes. Okay, so your turn. Okay, you're going to identify the domain and range of each function. Okay, so pause the video and try letter A. Okay, so domain and range, you're just going to list them. So my domain, again, remember, is my x's. So 2, 3, 4, 5, and 6. Okay, nothing repeats. We don't have to list it twice. Okay, and then remember, range is your y's. So 0, 1, 2, 3, 4. Okay, that's all that you're asking for there. Pause the video, try letter B, please. Okay, letter B is the exact same thing. Domain, okay, and usually with domain and range, we like to list them least to greatest, so our smallest to our biggest. Okay, so -3, -1, 1, 3, and 4. Again, notice none of them repeat. Okay, range, again, I like to list them from smallest to biggest. Okay, so I got -2 is my smallest, so I'll list that guy first. Then 1, and 2, 3, and 6. Okay, it's a lot nicer to keep them nice and neat in numerical order. All right, moving on. Example 2, we're going to analyze reasonable domains and ranges. Okay, so a function can model each of these situations here. Our job is to come up with what is a reasonable domain and the range. Okay, so remember the domain is your input, and your range is what you get out of it. It's your output. Okay, that might help remember. Okay, so let's look at letter A. or the first one here. A hose fills a 10,000-gallon swimming pool at a rate of 10 gallons per minute. Okay, so I like to also identify what two things are we really working with here. Okay, I see gallons and I see minutes. Okay, don't worry about just the numbers. Think about what two actual things we're working with. Okay, so if I input gallons, am I going to get minutes out? No, that doesn't make a lot of sense in this scenario. So my input here is going to be my minutes. Okay, based on how many minutes I'm putting in is how many gallons my pool is filled with. So here's how they describe it. So a reasonable domain is from 0 minutes to the time it takes to fill the pool. A reasonable range is from 0 to 10,000 gallons, which is how full the pool can be. Okay, so identifying the things you're working with, then putting numbers to it is how you want to work this. Okay, so let's look at another one. A restaurant needs to order chairs for its table. One table can accommodate 4 chairs. So again, what two things are we working with here? Well, I'm seeing chairs and I'm seeing tables. Okay, so which one would we probably pick as our domain? Okay, our x's. I would pick tables as my x's, okay, because I can't really have chairs without the table. Okay, so then let's look at some numbers. Okay, so a reasonable domain is from 0 tables to the number of tables needed. Okay, so tables we want as our x values. The range then is multiples of 4 from 0 to the number of tables needed. Okay, multiples of 4 because every table needs 4 chairs. I'm not going to order just a few. Okay, 4 chairs for each table. Okay, building off of this, we talk about continuous or discrete for the domain. The domain of a function is continuous when it includes all real numbers. Okay, so I can have decimals, I can have fractions, okay, that kind of stuff makes sense here. So then when I plot this, it would be a line or a curve. Everything would be connected. Okay, so the domain of a function then is discrete when it consists of just whole numbers or integers. Okay, the graph of a function is a series of data points. Okay, so let's look at the same two examples and think about if it's continuous or discrete. Okay, so Holes fills a 10,000-gallon swimming pool at a rate of 10 gallons per minute. Well, in the last one, we talked about that the domain was our minutes. So do you think minutes is continuous or discrete? Well, minutes are going to be continuous. Let's think about why. Okay, so can I stop a timer at 2.5 minutes? Absolutely. Can I stop a minute at 2.1 minutes? Absolutely. Okay, so I can include decimals when I'm talking about time. Okay, so then if I look at the other example, a restaurant needs to order chairs for its table. One table can accommodate 4 chairs. We decided that the number of tables was our domain. So is the number of tables continuous or discrete? Well, can I have 2.5 tables? No, you can't. That means this domain is discrete, okay, because we can only have a whole number of tables. Oh, your turn. You're going to analyze each situation, identify a reasonable domain and range for each situation. Okay, so please pause the video and try letter A. Okay, letter A, a bowler pays $2.75 per game. Okay, so the two things I'm working with is the game and the money. Okay, so does it make more sense for us to talk about money first or games first? Does the amount of money I have affect the games, or do the games affect the amount of money I pay? Okay, well, we're going to talk about the games. That's what's the important thing. Okay, so my domain is the games. Okay, which would be from 0 to whatever, however many games you want to play. So that makes the range the money. Okay, which we're paying $2.75 per game, so we're going to say 0 to multiples of $2.75. Okay, to however many games. Okay, so then I could extend this even a little bit further. Would my number of games be continuous or discrete? Well, this would be discrete, okay, because I'm not going to pay for a half a game. Okay, I have to play a whole number of games, okay? So that's another example there. Okay, part B, pause the video and try this problem. Okay, part B, we're talking about car traveling 25 miles using 1 gallon of gas. Okay, so what two things are we working with here? Miles and gallons of gas. Okay, so start the domain. What do you think you would do? Well, the domain would be the gallons of gas. Okay, and it would be 0 to however many you buy. Okay, so then if that's my domain, my range then would be the miles. Okay, and this would be multiples of 25, because that's what we're talking about there with the 25. From 0 to however many miles. Or, sorry, however many gallons. Okay, so then extending it like we did in the last problem, would this be continuous or discrete? Well, think about the gas pump. Do you have to pump exactly 3 gallons of gas? No, I could get 3.67 gallons of gas if I wanted to. So this domain would be continuous. All right, moving on. We're going to classify relations and functions. Okay, so the first thing we got to decide with some problems is it a function? Okay, remember, a function means every x only has one y. Okay, no cheating x's. Okay, then if it is a function, we're going to talk about whether it is one-to-one or not one-to-one. Okay, so the first thing let's look at is it a function? Okay, so remember, each x only has one y. Okay, I don't want any cheating x's. Okay, so I'm looking at my x values. Are any of them cheating? Okay, no, they're not repeated at all. So this is a function. Okay, this relation is a function. Okay, so every element of the domain maps to exactly one element of the range. Okay, another easy way to tell if something is a function or not is to make a mapping. Okay, you guys did this in 8th grade. Okay, you do domain and range, and you just list the numbers. Okay, so we had 1, 5, 7, and 8. And the range we had, again, I'm going to put them in order, -1, 0, 2, and 6. Then I can draw my arrows to see how they connect. Okay, so 1 went to 2, 5 went to 6, 7 went to -1, and 8 went to 0. If I look at my x's, is there more than one arrow coming off any of those numbers? Absolutely not. Okay, so this would definitely be a function. Okay, so now we're going to talk about what it means to be one-to-one. Okay, a function is one-to-one if no two elements of the domain map to the same element in the range. Okay, so this means no cheating y's. Okay, each y can only have one x. Okay, so when two or more elements of the domain map to the same element of the range, we say it's not one-to-one. Okay, so here, for it to be a function, we looked at the x's. For it to be one-to-one, you look at the y's. Okay, how many arrows does each thing have? Oh, they only have one, so we are one-to-one. Okay, so this is a function, and it's one-to-one. Okay, and I often will shorthand that's one-to-one. Okay, so there's the definition again. One-to-one, I often shorthand like that. So another way to think of this, we talked about function, meant no cheating x's. And then one-to-one means no cheating x's and no cheating y's. Okay, so nobody can cheat in one-to-one. This is what we like. Okay, so let's try a couple more examples. Okay, is this relation a function? And then if it is a function, is it one-to-one or not one-to-one? Okay, so notice this is a mapping this time. Okay, last time they just gave us a list of points. This time we have a mapping. So first things first, let's check to see if it's a function. Okay, I'm looking at my x values here. They all only have one arrow coming off. So this is a function. Okay, now we're going to check to see if it's one-to-one. So I take a peek at my y's. Okay, is 17 cheating on anyone? Ooh, 17's a cheater. They're dating 1 and 2. Okay, so just based off just the 17, this is not one-to-one. Okay, because 17 has more than one boyfriend. We don't like that. That's a cheater. Okay, so absolutely this relation is a function. Every element of the domain maps to exactly one element of the range. And then, since more than one element in the domain maps to a single element in the range, the function is not one-to-one. Okay, so it's a function because every x only has one y, but it's not one-to-one because the y's are cheaters. Okay, so I like to think of it that way, and I think it helps a lot. All right, your turn. Okay, you're going to try these two problems. Okay, is each relation a function? If so, tell me if it's one-to-one or not one-to-one. So pause the video and try letter A, please. Okay, looking at letter A, we check our x's first to see if he's a function. Okay, -2 only has one boyfriend. Okay, 3, oh, 3's cheating. Okay, they're dating both 6 and 7. This is not a function. Okay, and we're not even going to worry about one-to-one because it has to be a function in order to be one-to-one. Okay, so then letter B, pause the video, you're doing the exact same thing. Here's a hint though. You use the vertical line test to tell if it's a function. Okay, remember back to 8th grade math. Then we use something called the horizontal line test to see if it's one-to-one. Okay, pause the video and try. Okay, so to see if it's a function, remember a function, every x only has one y. So we can draw a whole bunch of vertical lines, and each vertical line can only hit one point. Okay, so this passes the vertical line test, so it is a function. Okay, you should remember that from 8th grade. Then to tell if it's one-to-one, we're doing the same thing, but this time we're using a horizontal line test. I'm going to erase these blue lines so we don't get confused. Okay, I draw horizontal lines, I can only hit the red line once. Okay, I only hit once, so this is one-to-one. Okay, and that's how you can tell. Right, so now we're moving on to something called constraints. Okay, constraints are, think of it as like cutoffs. I can only have these certain things. Okay, so the diagram here shows shipping charges as a function of the weight. Okay, so how much you have to pay depends on how much it weighs. Okay, so based on the situation, what constraints, if any, are on the domain of the function? Okay, well, let's think about this. Okay, I'm shipping a package. Okay, is there anything I can't ship for a weight? Well, an order must have a weight greater than 0. Okay, so the domain of the function is confined to values greater than 0. Okay, does it make sense to ship a package that's -2 pounds? No. Okay, so most of the time in the real world, most of the time, we constrain ourselves to 0 and greater. Okay, and most of the time negatives don't apply for a lot of things. Okay, so that's kind of something you might see a lot. We are going to constrain ourselves to values greater than 0 because negatives will not. All right, your turn. Pause the video and try this problem, please. Margaret has a monthly clothes budget of $50. She maps the amount of money she spends each month to the number of clothing she buys. What constraints are on the domain? I like to put this so the money, she's mapping it to the items of clothing. Okay, so this is telling me that the money is my domain. So is there any constraints on the money? Well, right here it tells us she only has a budget of $50. So I'm constrained to $50 or less. Okay, so thinking about the or less part, can I spend a negative amount of money? No. So my domain is constrained from 0 to 50 is my constraint. All right, so let's just sum this up real quick. Relation is any set of ordered pairs. Say special type relation is a function, so every x can only have one y. Okay, we use tables, we can use a list of numbers, sometimes we use these mappings that we're used to, and we can look at graphs to help see if they are functions or not. Okay, so homework page 93, you're going to do problems 13 through 23. As always, please come prepared with questions. See you guys.